So not all force problems get to be on a nice flat surface. So now we have to talk a little bit about what do you do when you have forces on inclines, which would be things rolling down a hill, sliding down at angles. And this is going to bring in components, trigonometry, and we're also going to have to do something a little tricky that will make things immensely easier, but you'll have to think about it pretty carefully. So first we'll start talking about the steps for problem solving. And that first thing is we're going to use a system that's parallel and perpendicular to the surface of the incline. And we're going to do that by kind of rotating the x and y coordinates so that they align with the surface of the slope and they're perpendicular to that surface. And that's going to make things a whole lot easier. You're going to go through and identify all the forces: normal, applied force, weight, frictional force if there is any. You're going to create a free body diagram. You're going to go through and find the components of the forces, keeping in mind we're thinking parallel and perpendicular, not x and y. You're going to determine known and unknown quantities from your problem, and then you're going to go through and find net forces. And so here's what I'm talking about rotating the coordinates. You got this nice little hill, guy sliding down it. It's got an angle of 25 degrees. And so we can simplify this by tipping the axes so that the surface that he's sliding on is the parallel piece and his normal force is the perpendicular piece. So the parallel pieces are going to be the net force and then the friction. And then the normal force and weight are going to end up being perpendicular once we break the weight into its component forces. So we identify our forces. So we have a normal force, we have a weight sliding down the hill. We've identified its motion. And we need to look at the angle. And it gets a little busier. You've got the components, and one of the things that makes this a little easier is if you look at the geometry carefully, the angle of the incline and the angle between the perpendicular component of gravity and the weight itself are going to be equal. And you can go through and do this with geometry if you wish, but basically whatever that incline angle is, we can work with in our free body diagram. As we set up our equation for parallel and perpendicular forces, and we get that the net parallel force, which would be mass times acceleration, is going to be minus the frictional force if there is any, and then the weight component in the parallel direction. The perpendicular piece is going to be the normal force going upward minus the perpendicular piece of the weight. And if it's not accelerating in the perpendicular direction, then that's going to be equal to 0. That little trick will be useful for solving a whole lot of problems. So we're going to have an example next. Alright, so I have an example for you with two kids taking a sled up a hill. The sled has a rider on it. One is pulling with a force of 100 newtons and the other kid is pushing with a force of 80 newtons. The sled and the rider have a mass of 50 newtons. And the question that we're answering in this example is, what is the acceleration of the sled? There's a lot of different questions you can answer. I'm going to go through a little bit more detail than you would need to answer this specific one, but it's kind of a general setup for almost all of the force questions on an incline. So first thing I do is sort out the information with a doodle and then a little diagram, working my way up to the free body diagram. I have my two applied forces pushing up the hill. I have the normal force of the surface pushing up on the sled, and then the force due to gravity pulling straight downward. And I've listed out what's given in the problem. The applied force of one kid of 100 newtons, the second kid of 80 newtons, my angle of my hill, which is 20 degrees, the mass of the sled and the other kid is 50 newtons, and then I'm looking for the acceleration. So taking it one step further, I've got my free body diagram, and I'm starting to look for the components of the force due to gravity because it's not perpendicular or parallel to anything. It's kind of off on its own little 20-degree angle. And so I know I'm gonna have to find those components, and then I need to figure out what else I know and don't know. And so looking at all the parallel forces, we have MA, which would be the net force. And in this case, the sled they're dragging that sled up the hill. So it's going to be the sum of the two applied forces minus the parallel component of gravity or weight. And then in the perpendicular direction, the sled's not accelerating up and down in the perpendicular direction. And so that's going to be 0, and that is the normal force pushing up and the perpendicular piece of the weight pulling down. And then once you have those two equations, you start figuring out all the things that you can find with what you know. And so I started with the perpendicular piece. The perpendicular component of the weight is mg cosine theta. Plug things in, get 460 newtons. And from the equation I set up using the net forces, I know that the normal force is going to be the negative of 460 newtons. They're opposite and equal. And then when you look at the parallel piece, you get the weight is going to be mass times gravity times the sine of 20, and you get 168 newtons. And then I have the fact that the applied forces are just the sum of those two, kids pushing, one pulling, and then you get 180 newtons. Keep chugging to put it all together, and you can get mass times acceleration is equal to the sum of the applied forces minus the weight. So it's from that equation right there, and I plugged in my 50 kilograms and worked my way around and got acceleration is 0.24 meters per second squared. You may end up not having all these parts. You might have to go through two equations and two unknowns, but you do have two equations. So you could do a two equation and two unknown scenario. The other thing you might be asked to find is something with kinematics. So now that we know the acceleration, let's find out how long it's going to take them to move the sled 10 meters if they start from rest. And so we know they started at a 0 point. They went 10 meters. Our acceleration is 0.24 meters per second squared, and the initial velocity is 0. So we are going to match up what we have and what we need to know, and we're going to use this equation right here. Plug everything in, and we get that it's going to take them a little over 9 seconds to move the sled 10 meters. Hope this helps you guys. Bye-bye.